I'm starting a new YouTube channel called FN-DSA Group that's dedicated to my services for consulting and education on cybersecurity. For those of you who have listened to my previous videos, I used to post videos out of a mixed channel. Also a cyclist and a yogi. So I used to put a lot of videos on yoga and cycling, but I decided to make the context separate, content separate, and start this channel uh, dedicated on security, AI and security, cryptography, and those type of things. So today, I want to talk about the conference, PKI Consortium conference that happened yesterday and the day before in UT Austin, Texas. This is my take on the conference. I'm not talking too much about the quantum computers itself, but I just kind of really like this picture, so I like to put this picture on all of my post-quantum cryptography. So this talk almost entirely is on post-quantum cryptography. So a few disclaimer first, and thanks. First of all, thank you to PKI Consortium for making the registration free and have a very great streaming service that I could just listen to, jump between the two simultaneous sessions back and forth as soon as I got bored or I felt the other one had something more interesting to say. They also facilitated live and remote Q&A, which was great. You could ask questions even from thousands of miles away. All the slides that I'm presenting here, they're all based on screenshots, and I intentionally did a screenshot a picture, including the picture of the author and the affiliation, so there are no attribution or copyright issues. And obviously I could only attend one session at a time, and I did some hopping back and forth, but my view, my take is based on a single person trying to attend these sessions. And the videos will go live hopefully soon on their own YouTube channel. Most of the talk speakers, they had slides, except Scott Aronson had a very interesting talk about quantum computers, and a lot of it went over my head. So I encourage you to listen to that. Nothing that went against too much against what we knew, what Jensen said at his discussion, at his presentation last week, which made the quantum computer companies crash. Basically, you can kind of listen to that and take this at your own understanding. Some of the cool things that I heard was, if you can't be quantum safe, be quantum annoying. What does this mean? Well, people are still debating how many qubits you need for breaking RSA or other things. And the idea is, well, okay, if you're sort of on the fence as far as how long does it take, just be more annoying and change your keys more often. The other thing is, a lot of people talk about PQC migration, making it graceful because they're selling you some kind of service. It's definitely not graceful, but people say that, yeah, you just try to make it not so horrible. And there is some discussion about the long tail of application and devices that will be very hard to migrate. I have a little slide on that. And the other interesting one was that NIST very explicitly came out when people asked question. I think I asked that question. The difference between NIST and NSA is like NSA focuses on national security systems, but NIST doesn't, and it focuses on many other applications. And then some updates on how PKC is making progress with web traffic and TLS from Cloudflare, and some really interesting things from NVIDIA, which sounds like NVIDIA is bringing AI to quantum computing and GPUs into post-quantum cryptography. So I decided to start with NVIDIA because, again, it was, as this speaker also said, Yarkin, despite what Jensen said about quantum computing, NVIDIA itself looks like it's working on the ecosystem. They're not making qubits, they're not making quantum computers, but as usual, they're kind of selling shovels to people who are in the gold rush. And the interesting one here is that they're making what they call supercomputers that will connect quantum hardware and basically, okay, so basically what you can see here is that they're talking about qubit agnostic systems, which is basically anyone with any type of qubit technology can come here and play, and basically they're connecting. They're trying to connect all type of quantum computer hardware to each other. They're also talking about hybrid algorithms. This is on the software side. The first one is on the hardware. The second one is the software, which is people are already developing algorithms, software algorithms that are dedicated for running on quantum computers. So they're talking about these supercomputers being able to run on hybrid algorithms, both using GPUs as well as what they call QPUs. So that is basically running both quantum as well as classical computers and algorithms. So this is very interesting, making it hybrid, making it agnostic to the hardware as well as the computing paradigm. So that's what NVIDIA is up to. To me, it comes back to selling shovels, basically. It's like, I'm making it qubit agnostic. I don't care which one is going to win as far as which quantum computing technology is going to get ahead. We'll just make it qubit agnostic. The other interesting thing here that I picked up was, it kind of feels a little bit like CI/CD here. They're talking about both development of quantum computers as well as deployment of quantum computers. So in the development, they're talking about using AI for design of quantum computer hardware, basically doing noise modeling, doing error correction, doing things that basically everyone is trying to control the qubits state, and reduce the amount of noise so that you can basically trust and capture what the computing environment produces. So this is on the development side, and this is on the deployment when it's actually running, helping with the error correction and helping with calibration, control, and those type of things. So this goes a little bit over my head, but it kind of sounds like the development side as well as the deployment side, but obviously there's a lot of physics involved and a lot of manual analysis involved as far as what you need to do to get rid of the noise and error correction, and here they think AI is very useful, and that's what they're working on. They have a paper, there's so many authors here, but that's the title of the paper, and I think it was published very recently, and just captured the screenshot of the paper here for people who want to go dig into that. This was very interesting, and just when you thought you had heard of enough of Gen AI, we started with LLM and then we went to agents, and this one is talking about basically something like a large language model, but in this case some kind of large circuit model, which basically means it looks at the quantum operations and it generates quantum circuits. So like LLM will take the words in the dictionary and in the language and turns it into embedding, and then uses these embedding to compare a similarity between the language and what it finds in their data, and try to generate the best guess for the answer. In this case, it basically looks at quantum operations and try to generate quantum circuits. So this is very interesting. This is a very interesting paradigm for generative AI, but not for language, but for quantum circuits. And this was also a very interesting area. St. Jude, of all places, and University of Toronto with NVIDIA, they're working on sorry, this is coming a little bit late with my animation, but they're talking about drug discovery application, which is a very nice thing to hear. The other thing NVIDIA was talking about, which was surprising but not surprising, was the fact that the GPU is very good at parallel mathematical calculations. They're designed to do matrix calculation, which is what the modular lattice crypto algorithm really need in terms of acceleration. So you look at any of the silicon vendors that are selling post-quantum crypto accelerators, especially in the modular lattice, they're using this NTT accelerator. And NVIDIA basically talks about using the GPU for this purpose with kind of native use of GPU. The other thing is they also talked about, I didn't capture the slide fast enough, but they also talked about, due to the fact that there is a large frequency of cache and memory operation for the GPU, the power trace that is created when the GPU is running these algorithms, it's very noisy, so it's very difficult for analysis. So the modular lattice algorithms have been said to be very sensitive to side channel analysis, which is like, power trace analysis and timing trace analysis, because people can see when the processor goes to the memory and fetches some intermediate parameter to calculate the keys or other things. And based on that, they will be able to do a lot of guesses. But when the power trace is very noisy because of the way GPU operates, it will make it more resilient towards side channel analysis. So again, I didn't capture that fast enough, but that's what the claim was. They also had a lot of benchmark on ML-DSA, which is the modular lattice digital signature algorithm. And I leave it for you guys to go check this talk when the YouTube video comes out. It sounds a pretty interesting result there. Okay, so moving on to sort of where the standard is at. This guy is he was the manager for cryptography technology group at NIST. I forgot to put his name here, but you can see it on the conference page. He talked about the algorithms. He mentioned the 3 that were published last August. He also talked about the Falcon, which is a floating point algorithm. But the interesting part is he forgot to talk about the LMS and XMS, which are the sort of the ones that were standardized very early on, the hash-based algorithms. They did NIST admitted under misguided restrictions on state management. So these algorithms are very sensitive to state management, and NIST had previously had restrictions on the backup or the duplication of the states at the hardware security modules, and they realized that these restrictions made these algorithms almost impractical for anyone. So that's funny how they forgot about that one. And NSA also had a presentation that I missed, but I captured maybe like 30 seconds of it, where they were talking about the need for use of SHA-3 in secure boot environment. And that is also pretty weird, because despite the fact that we really needed SHA-3 for those type of applications, SHA-3 was forbidden for use in those type of signatures. Anyway, so some, I guess NIST and NSA are realizing that some of the restrictions and guidance that they provided early on is proving to be impractical. This is this guy, I forget his name. I didn't put it in there, but he's from Entrust. Um, and he made a very nice Venn diagram where here you can kind of see if your head kind of spins when you hear all about different countries, like BSI is from Germany and the US and UK and all other people. Different countries have different algorithms that they require, and typically it looks like the US and Australia are the most restrictive, with the most secure algorithms of all these versions being in US. And you can see by the parameters, for instance, for the digital signatures and the key encapsulation, the highest parameters, the highest category of security is for the US, whereas other countries allow a bigger set of algorithms here. And this is also a very nice algorithm, Sphinx, and this is not allowed by NSA, but other countries are using it. So moving on, in case someone wants to have all these numbers in one place, you can compare the size of the public key, private key, and signature, and the security level for these different algorithms. Remember that these two are classical algorithms, RSA and ECDSA, and these two are the ones that were standardized last August. And this is Falcon that is on the way to standardization. And you can see some nice properties here. Signatures are smaller, even though the private key is bigger than these algorithms. So a lot of people were settling out on this algorithm because the restrictions that I talked about with the algorithms that proved to be impractical. So now these show that there are smaller signatures, smaller public keys, but bigger private key. And the other thing that's good to see is for these algorithms with different categories, they compare them with other cryptography algorithms that are well known, AES and SHA. So you can look at this at your own leisure, or if you need a reference, you can come back to this. This is another one. This is from, I think it was from Cloudflare, and this is their own practical data. The information from NIST and others, they're just sort of theoretical standards. They don't cover, how long something takes, and this is basically showing how long the CPU takes to do something. Obviously, you need to know a lot more about the CPU to figure out, but the clock speed and those type of things matters. But they use this algorithm, ML-DSA 44, which is the weakest category, as the baseline, and then compare everything else to that. So as the interesting part is, you can see that this new algorithm that's on the way to be standardized, it's faster than ML-DSA. So verification is important for secure boot and secure firmware update, whereas some provider of the software or the device performs a signature and then load that software into the device, and the device needs to verify every time it boots up. So verification is very important for device boot up time and boot performance, and updating its own software, whereas signing is more important for the infrastructure side. Unfortunately, this algorithm, although it's fast, They decided not to put this in the national security system like US NSA because they thought that implementation is going to run into a lot of issues because it's using floating point arithmetic, which is kind of hard to do. Anyway, so what else? The NIST also talked about the impact of these new cryptography algorithms, especially the signature algorithms, on what happens on the internet. So this one is basically saying this algorithm, which is the weakest digital signature algorithm, is going to add about 14K because of the sizes of the signature, and this will cause issues with for instance today, all the web traffic is secured using TLS, and TLS 1.3 is the latest version, but TLS has restrictions as far as the size of the packet that it allows over Ethernet or IP networks. I have some more slides on this, so I will cover this later on. So that's why they're kind of looking for a new set of algorithms with smaller signatures. Again, Cloudflare was talking about Cloudflare because they're a hosting company. They're a network. They're sort of a internet hosting company. Host a lot of people's web services, similar to Akamai and others. They have a good control. They have a good view of what's happening on the internet, and they see that on their own servers, hosting web traffic towards normal users, what they consider or assume is a human user on the internet. They saw that they think about 30% of their traffic has now moved over to post-quantum encryption algorithms. Again, I have data on that, and they also have some studies showing the sort of degradation of TLS performance based on the size of the signature. So they basically, in a 2021 paper, they said they found that for every kilobyte added to the TLS handshake, it's about 1.5% degradation of the performance. Again, I have more data on this, so I'll move on. Key Factor is a company that provides digital certificate services, among other things. So they had some interesting discussion. They look at the services over internet that provides the digital certificates to other people. HSM is a hardware security module that is used to perform cryptography needed for issuing digital certificates. So a lot of people can't afford to have hardware security modules, and they relying on cloud-based HSMs for their certificate needs, like AWS and others are providing that. And basically they examined a whole bunch of HSM vendors. They hid the name of the HSM vendors because they wanted to protect the vendors, but they basically showed data HSM1, HSM2, HSM3 without mentioning the names. And they saw that even though this year was the year that the government wanted people to start moving to 2025, there are not that many vendors that are actually supporting ML-DSA. Sorry. And then a lot of them don't still support LMS, which was the first one that was standardized. And also they measured the speed, and they saw that some of these HSMs are extremely slow. They maybe support 1 signature per second, which is pretty bad. And many had restrictions over, let's say you want to sign something, your piece of firmware or anything, and you will send this to them to sign for you. And they saw that some of these HSM vendors had a restriction on the size of the payload. So basically, you kind of need to first hash whatever it is you want to sign and then send the hash over them to reduce the amount of traffic. Um, Anyway, so this is another nice slide and you can kind of look at. I don't have a lot to add aside from this is a nice slide for people who want to see what type of algorithm will be used in what application, whether it's a browser or email or that sort of thing. So I don't want to comment too much on this. This was Thomas Gustafson. He calls himself Chief PKI Officer for Keyfactor. A little bit of discussion that is interesting. This is from IETF, who's standardizing different types of certificate and PKI. And because of post-quantum and classical algorithms, they're sort of, we will live in a migration period, probably, I would say probably a decade, where people have to slowly start from an environment where they implement both classical algorithms and the post-quantum algorithms. So these things have to live side by side. So there are different ways of combining these two. This one is proposing that you will use a root that has a hash-based algorithm. This is Sphinx. And why? Because Sphinx is an algorithm that has a very large signature size, so it would be very difficult for the internet to carry these. Let's say you want to do a TLS and you have to present these certificates to the other side. This would cause a lot of traffic bandwidth. So it's better to, but on the other hand, the root CA is typically embedded into the configuration. You don't need to send it, you just send the issuing CA and the cert itself. So on the top, they're using hash-based algorithm for multiple reasons. One is, this one is a stateless, you don't need to keep the state. And number two, hash-based algorithms are trusted. The technology existed for about 40, 50 years. And in case you don't trust the algorithms that needs the standardizing every 6 months or a year, and they may break, you keep that as a root level. At the lower level, this is a sort of a mixed key. So you can see that there is a signature that is using both a new and an old algorithm to do a signature. And this is very difficult in operation, as they mentioned. Why? Because you probably have different hardware security modules that are supporting each one of these algorithms. So how you're going to apply a signature from two different hardware, it's pretty difficult to do. The next option is they call multiple certificates, and in this case, you just run two different set of certificates in parallel. And this basically, sort of the operation people, the people who issue certificates, sounds like they're just kicking the can down the road. And for operation is easy. You may have a set of people doing this and a set of people doing that. But at the protocol level, this will be very difficult because the protocol has to decide which one of these two to use. And it will be they say it will be only good if you have an online algorithm, which is like two sides negotiating, deciding which algorithm to use. But if it's a case where somebody's, signed something and somebody later needs to do something with that, there is no possibility of negotiation, so this will be difficult. And then they kind of look at different applications, and they think TLS is handled pretty well. And this is cryptographic, I forget, message signing. I forget what this was, but this had to do with both signing and encryption of large files. And this is the token that is used for all the web security and authentication authorization. They're not very clear if this will work with multiple certificates. So I need to speed up a little bit, and this was the composite case. The composite case is 2 keys and 2 signatures, and they feel like this is a good thing for, okay, so this not backward compatible very well, but it's very nice in a case where you just take one protocol, one algorithm in the protocol, and replace it with something else. So it's a good drop-in replacement. Just lift one and put the other one in without having to worry which algorithm is gonna run. This guy Panos is at AWS. I think he was one of the guys who worked on the LMS standardization. This is the rest. A few more slides is talking about the impact of the fact that you would have so many signatures on a certificate chain for TLS, and what impact would that have on the performance. Actually, he started his talk by how this whole 15 kilobyte of ML-DSA that I talked about earlier, how that would impact the web user. And he just talked about a web page. Let's say someone loads a web page, and there are various sort of metrics for the web page to consider. And time to first byte is when you receive the first byte on the web page. Let's say you're looking at the web page on your browser on your phone. These are the things that come in order. So time to first byte is just the first byte for that page. The user may not see anything. First content to paint is, let's say, if you remember the old dial-up, first the text would show up, and then the picture would take a while to load. So the very first thing that the user sees is the first contentful paint. DC is when the entire document is complete, the whole page will show, and LCP is the largest contentful page. Maybe it's a video or something. So he kind of made a calculation and is basically showing the impact of, let's say you have a PQ post-quantum algorithm signature that is adding 15 kilobytes of data for your TLS exchange. And this basically, this basically looking at someone who's used a 4G link with 9 megabit per second downlink, and in that case he just does the physics and says, with that kind of speed and that addition to the signature size, the TLS is going to get smaller by 8%. And then each one of these have the effect of about 1 to 2%. So basically that's on a web page, and he just made a comparison for someone who's let's say using Instagram, and basically how much does this mean if someone is outside and has a 1 megabit per second link, and how would that how would that impact the transfer time? And for TLS in that case is a 66% slowdown, which is huge. And then he's talking about all the other things that needs to happen for that picture to show up when somebody's just scrolling down on their Instagram. And you can see the lookups and the handshake and the HTTP, and this basically come down to 19 seconds. And basically this means this user scrolling down these pictures on Instagram, his scrolling would be slower by 13%, which is huge. The next one was also a talk, very interesting, nice talk from Cloudflare on PQC migration, and I picked up the lessons learned and put it on the first page, and then I go through all of these. So the first one is obviously the size of the keys and the signature, what side effect will have, and start testing and make sure what impact this will have on your system. The second one was just running the protocols and writing software. In the software, you make sure that you accommodate for new fields, new extensions, new algorithm identities, and don't hardcode anything. And the third one is the cases where somebody had made an implementation but is not following the standards. I have screenshot examples from each one of these cases. So the first one was, this is not one of the lessons, but it's just a very interesting observation. This is similar to what I showed before. About 30% of Cloudflare connections are on PQ post-quantum. They also moved most of their internal connections inside Cloudflare deployment to post-quantum. But on the other hand, it's when people are hosting some kind of service on Cloudflare. Let's say I have my, Avances group security server or service running over there. They saw that in those cases, what they call origin servers, it's only less than 1% of organizations' actual servers are supporting post-quantum. So it's a little bit depressing on the sort of prevalence of PQ outside these people who are more professional on web hosting. They noticed that key agreement is a lot more ahead than digital signatures. So key agreement is basically how the algorithm, when you decide what sort of keys you need to use for encrypting data and those type of things. Whereas digital signature is mostly about proving who I am and who you are, testing the certificates to see that we are authenticated. And they think that this is not as prevalent and it's more challenging because they think a lot of people are involved, browsers, server operators, and certificate authorities and that sort of thing. So they think signatures is a lot harder. The other thing here is, again, this goes back to the lessons. When you have larger keys, today the internet is running on IP, Internet Protocol, which in turn is running on Ethernet. Ethernet has a maximum transfer unit of 1500 bytes, which means if you have signatures that are 15 kilobytes, you sort of have to break these packets into smaller packets. So they're kind of trying to show this by client H and then LO is coming after here. So you have to break these into fragments, and they notice that there's a lot of servers or middle boxes or proxies that either cannot handle the fragments well, or if they can handle the fragments okay, if something happens in the network and some of these fragments don't come in order and out of order, that's another case that they're not handling. But overall, this is very small percentage of the servers. It's like maybe less than 1%, but because they're seeing a lot of traffic, for them that's a lot. These are also another case where the internet is full of load balancers, and here's you have a load balancer that is sitting in front of two different servers. One is supporting post-quantum and the other one doesn't. That's another issues, and that's why they call it long tail. I heard the term ossification here, which is basically resistance to change because you have older servers, you don't have money to change them, or you have older softwares and you haven't been updating it, or maybe they cannot support a new algorithm. So ossification came into the discussion several times. Okay. It looks like I did some mess up with my, this is a different set of slides. I'll mess up my animation. This was a case where, let's see, I might skip that one. So this one was a case where there are extensions in the protocols, but the software cannot handle these extensions very well. So they basically pointed out to a very nice process called grease, I guess, and I don't know this is grease or not, but it's WD-40 that people used when something is kind of not moving very well. So the idea here is maybe you have a client somewhere out in the world that is pretty advanced, is supporting a new algorithm, but there's a server that doesn't support those algorithms very well. So even if the server is not supporting the algorithm and you have to use some old algorithm, if you still support, if you still send their extension and say, hey, this is what I support, I guess someone will uh, pick this up and think that it's going to add that support later on in the future. So I guess you're kind of creating a to-do list for someone. Um, NIST has a Cybersecurity Center of Excellence, CCOE, misspelled up there, for PQC migration. The reason I put this on there is because I wanted to say if you have a project and you're looking for vendors, it's good to pick it from here, because if these people are part of this center of excellence, that means they're actively working on something. So they're trying to be a little bit more selective, and I don't know if is joining this is at this point is possible, but anyway, you can probably subscribe to various things here, listen to their monthly or quarterly updates and things like that. Um, these are some things you can kind of take a look at in terms of migration, the components that are needed, nothing major. You can just stop the video and check this here, but it's talking about software and hardware acceleration and libraries and protocols, all the things that you have to do. Um, Now, in terms of migration, um, and why people don't migrate. I mean, I wish something like this was around when I was getting beat up for not making decisions fast enough in my previous jobs. Somebody actually decided to make a PhD project out of this. I am being a little bit cynical, and they basically were studying why PQC migration will have difficulties and what needs to be done. I guess maybe if you set up a really fancy consulting service and want to go tell people what to do for migration, this would be helpful for you. So sort of they looked at the challenges for migration, and basically they were thinking about creating a questionnaire tool and figure out different dimensions and how to tackle these things in terms of migration. So I'm talking a little bit into abstracts, but this you can kind of see some of their motivations here. But the thing that I thought was pretty interesting is the next slide. They kind of created a matrix, and in the matrix, I'm writing some of these things down in case it's not readable, but they're kind of adding all these challenges on the rows, like things like uncertainty in the standardization process. This is something that the countries and standardization bodies need to do. Whether technology is available from a vendor, whether hardware is available, QS in this case is quantum safe, I guess, or software is available, whether you have technical skills within your organization, technical skills within your customers' organizations or your partners. Obviously, you're not alone in this journey. The lack of urgency, some executive doesn't think this is very important, or it is. Lack of collaboration, these things require collaboration. You need the vendor to HSM vendor to sign your to support a signing algorithm if you want to sign messages or firmware or that type of thing. So it's important, but at the same time, there is more competitiveness than collaboration in the industry. So anyway, they kind of put all of these challenges on this row, and then they created a matrix, basically same thing on over here, and they try to see which one is related to which one. So basically, if this is a channel, which one is influencing another one, and codependencies and things like that. So they moved on. They talked about this for like 5-10 minutes, and they put ones and zeros, and basically a lot of number crunching. But obviously, I I personally don't think you need a PhD to know that um, you don't have a single challenge, whether it's lack of skills or whatnot, that is the only challenge. They're depending on each other. If one is not removed in time, it affects the other one, and that sort of thing. So anyway, this another chart that is showing all this. So if you want to go tell your boss it's not all your fault, if they're listening to reason, then you can show something like this. But in general, I thought that was interesting that somebody would spend a lot of time doing a PhD on this one. This one, on the other hand, was more interesting. Again, migration, again from, I think it was Entrust. And this is the same guy, very knowledgeable guy, and talked about migration. I have shown these things in my previous slides, like what kind of data you have, who you're selling to, when you're making a decision on whether you need to move to post-quantum or not. But this one, I didn't think about before. It's like, okay, you have a large infrastructure, and you have a IT organization, and you have a product security organization, and you have a budget. All of that points to how fast can you upgrade things, and can you upgrade one side without updating other things. And then also the protocols that they're using. Let's say you're using something like a TLS, and if one side is using a good algorithm and the other not, how susceptible this algorithm is to the downgrade. And this is the final slide. We're talking about how, the long tail of X509 is a certificate standard. Is basically, that's where post-quantum algorithms will get into the real life in terms of establishing connections, whether it's the web or whether it's your VPN, your code signing for firmware integrity, Wi-Fi, all that. And this is, they think, okay, this is things that you have to do right away. Usually this happens faster than others, and the long tail is stuff like your smart card to get into the building, and your whatever is on your password and all that. And I think this side is going to be very hard, because these are smaller devices, these are well spread, and it's very hard to bring them in and basically try to change these algorithms. So this is it. It took a little bit longer than I thought. It's about 48 minutes, but I hope you enjoyed it and it benefited you. And again, thank you for listening to this talk, and please subscribe if you like this. And basically, like I said, I provide consulting services. You can reach out to the address, email, contact that I have on there. Thank you.